Today we're going to be starting our unit on two variable data. We call it bivariate data. Suppose that a real estate agent wants to study the relationship between the size of a house and its selling price. It is reasonable to suspect that the selling price is related to the size of the house. So specifically, we expect that the larger the house, the higher the selling price. So a good way to visualize this is with a scatter plot. So in a scatter plot, we take one of the variables for the horizontal axis and one for the vertical axis. And usually we want that, what we call that the explanatory variable, the one that's affecting the other one to be on the horizontal. So if we look at this one, we have the size as our horizontal axis and our selling price as the vertical axis, because she's suspecting that the size affects the selling price. Now we can create these on the TI-84 and on the NumWorks calculator. So I will show you how to do both. So in the TI calculator, I would enter in my data, the one I'm expecting to be my explanatory variable or the independent variable, and the dependent variable, the one that's being affected, in L2. So I've got L1 and L2. These instructions are for the TI. So you enter your X values in L1 and your Y values in L2. Then we're going to go to stat plot, which is the second feature of Y equals. So second Y equals. And before we have used the histogram and the box plot, but this time I'm going to choose the very first option. It's a scatter plot. Now I need to make sure it's on, and we have a scatter plot, and then we're going to press zoom 9. Now this mark, you can change your dots to be squares, whatever you want to look at. So I'm going to press zoom and then go to zoom stat, which is number 9. On some of them, you may have to arrow down a little bit to see it. And we can see that scatter plot. This is really important to be able to see the data, to be able to know what kind of relationship we have. Now, if you're using the NumWorks app, let me go back to the home screen. Statistics here is for one variable data. This next one, you notice it has dots, kind of like a scatter plot. This is a regression feature. So I'm going to press OK here. In this menu, I have X and Y. I do have it tells me which one to go where. And then all I have to do is press this back arrow and go and highlight graph and click OK. It automatically affects the window. Now it does some other stuff too, but I can see the scatter plot, and then it guesses what kind of pattern it's making, and it puts in a line for that. It also gives me a whole bunch of stuff at the bottom, which we'll talk about in a little bit later. So the larger sizes tend to associate with larger prices, and smaller sizes tend to be observed with smaller prices. So we consider this a positive relationship or positive association, however you want to word it. In addition, the points tend to cluster around a straight line. You could see it really good on the NumWorks calculator. We describe this as by saying that the relationship between the two variables is linear. If it looks like it's a straight line, it's linear. Therefore, we can say that the scatter plot exists a positive linear association. It's going up, so it's positive. So like slope, positive, and it looks like a line. Now we could have other types of associations. See here, we have another positive association. This would be a negative association. It's going down. Now we could see that this is kind of spread out a little bit more, and so we can start talking about whether the relationship is strong. And the numerical measure for strength of a linear relationship is called the correlation coefficient. Now there's a couple of different equations for it. They look really crazy. The most frequently used looks like this. Oh my gosh, it's really a crazy one. Remember, this means we're going to add them up. We do x minus x bar. So each x value minus the mean divided by the standard deviation of the x's. And then y minus y bar divided by the standard deviation of the y's. And we multiply those together and then we add them all up. And it takes a long, long, long time. Well, our calculators can do this for us too, which I'll show you in a second. Now, this value is always going to be between -1 and 1. It's represented with an R too. I should mark that. It's an R. The correlation coefficient does not depend on the units of the variables, and it doesn't really matter which variable is X and which one's Y, but it will only measure the strength of a linear relationship. Now, we have to be careful. It is sensitive to outliers and can be really misleading when outliers are present. So that's something we have to be cautious of. Now, as I said, we could do this by hand. I don't really want to. I'm going to go ahead and show you how to do it in the calculator. Now, on the NumWorks calculator, if you look at the very bottom, it has an R value, and it's hard to kind of see, but it actually gives me what R equals. I've got a glare. There, it gives me right there. But I'm going to show you how to do it in the TI as well. So the NumWorks calculator automatically gives it to me. Now, if I'm doing this in the TI, which I believe I have instructions on a later page, I should have had them right there. The way I can do this is I'm first got to check my mode. So there's a feature that has to be turned on for this to work. So you need to press the mode button and check that the stat diagnostics are on. When the calculators are reset, that automatically goes to off, which I hate that it does that. But we want the stat diagnostics to be on, or else it won't give us this wonderful little shortcut on. Now, I'm going to press stat again and arrow over to calc. Oops. And we have a couple of options to pick. So stat calc. We assume that this is a linear relationship. There are two markers that say linreg, and AX plus B. That kind of looks like Y equals MX plus B. Now, a lot of the homework is going to actually use this one, number 8, where it has the constant plus a number times X. So we're going to use that one. Now, this is our X list in L1, Y list in L2. You can even store the equation. We'll talk about that more in the next section, but I'm going to go to calculate. And it gives me R at the very bottom. It's the same value I got on the NumWorks calculator, by the way. And all that good stuff that it showed, I don't know why I went that many, is also shown on the NumWorks calculator. So it gave me a positive number, positive relationship. And the closer it is to 1, the stronger it is. So if we thought about these values on kind of a scale, they go between -1 and 1. If you had a 1, that is a perfect positive relationship, like all the dots line up in a straight row. -1 would be a perfect negative relationship. They line up in a straight line. Now, 0 would be no relationship. So the closer you are to 1 or -1, the stronger the correlation is. And the closer you are here, the weaker it is. So let's look at some pictures and try to talk about what kind of relationship we think this would be, what value we would give it. So I've got a whole bunch of pictures here, and I want to talk about these different, whoa, my camera fell again. What kind of relationships we have here. So let's talk through them. Which ones look like they're positive? Well, this one looks like it's positive. This one looks like it's negative. This one looks like it's all over the place. Does it look positive or negative? Not really. This would be R equals 0. I don't see any patterns. This one's negative. This one's positive, but not really good positive. This is another positive. This one's negative. It's going down. This one's negative, but not as good as that one. And this one's positive. Now, if we talk about the strength, let's look at the positive ones first. Which one of these has the strongest positive relationship? Well, this one, this is almost a perfect line. I would estimate R to be even better than we had before. I would say it's like a 0.98. It's really strong. Now, out of the other positives, we have this graph, and this graph. So out of these, I would consider this one to be more positive. Maybe this is an R equals 0.8. It's still strong, positive. These two I would consider weak positives. Which one is stronger out of these two? Well, I'd assume this one. I might go with an R equals maybe a 0.6 on this. And this one may be a 0.4. It's kind of a weak relationship. Now let's look at the negatives. Which one looks like the strongest out of the negatives? So we have all our positives are done. Out of the negatives, this one looks really strong, but not as strong as that. So I would assume this would be a negative 0.9. It's not quite as strong as that one, but it's still stronger than some of these other ones. The next one that I would pick as a strong would be this guy. Maybe I suspect this one is like a negative 0.7. Now I've got two more negatives to estimate. We have here and here. This one seems kind of weak. Maybe it's a negative 0.3. This one's kind of weak too. I'm going to guess this one's like a negative 0.6. So you can see that we can kind of estimate their strength with those numbers. 0.9 is pretty strong. 0.98 is really strong. 0.99 would be super strong. Now be careful about talking about correlation and talking about causation. A group of elementary school children took a vocabulary test. It turned out that children with larger shoe sizes tend to get higher scores, and smaller shoe sizes got lower scores. As a result, there was a large positive correlation between vocabulary and shoe size. But does that mean learning new words causes one's feet to grow? Or having larger feet makes your vocabulary increase? There's not a causation there. And I'm going to share a link to a website that talks about some really crazy correlations that people could assume are causations.